Hello students, today I am going to talk about variance of a random variable. So you know that for a set of numbers, mean represents a measure of location, and for a random variable, the mean is the expectation, Ex, expectation of x. Now, for a set of numbers, variance is a well-known measure of dispersion, variance and standard deviation that you know. Similarly, for any random variable also, we can define the same measure of dispersion because a random variable is a function, and so it is taking different values depending upon the outcomes of the random experiment, and we can assign probabilities to the different possible values of the random experiment. So we would like to know how much variation is present in the values of a random variable. So variance is used to measure the amount of fluctuation or amount of variation in a probability distribution or in the values of the random variable. Here, of course, we assume that the Ex square is finite. Now, if x is a simple random variable, then there is no need for this assumption. But if x is any other, if x is not simple, that is, if x can take infinitely many values with positive probability, then of course this assumption is needed, because we can give examples of random variable which takes infinitely many values and Ex square is not finite. Anyway, that is a technical part. But so as of now, let us concentrate only on random variables that is either simple, or even if it is taking infinitely many values, it satisfies this condition. So number one point is that whenever you have such a random variable, there is an inequality that mode of the expectation square is less than equal to Ex square. This is known as the Cauchy-Schwarz inequality, or also the Holder's inequality. Now, here is a food for thought, that can you tell me what is expectation of x minus expectation of x? So this is same as if I sum the deviations from mean, what will be the sum? Now, variance is defined as Ex squared minus expectation of x whole square. You can also define it as x minus expectation of x whole square. Now they both are one and the same, under the assumption that Ex square is finite. Now I generally define it first Ex square minus expectation of x square because of this Holder's inequality. Now of course this would be making more sense, that x minus expectation of x whole square, expectation of that. Now what is x minus expectation of x? This is the deviation from the mean, and it is the square deviation from the mean, and you are taking average of that is the expectation. So this is the average of the square deviation of the mean. This is similar to the data definition that you have studied for variance for data. So if I have got n numbers x1 x2 xn, their mean is x bar. So how do we compute the variance? We compute xi minus x bar whole square and then average it over 1 by n. So that is like the same expectation of a simple random variable. That is like the variance of a random variable which is taking the values x1, x2, xn, each with probability 1 by n. Then also you will get the same formula. Now there are some other things mentioned like the covariance. Let me not get into this. I will share this note, but let me not get into covariance in this presentation. So let me go to properties of variance and expectation. So if x and y are two random variables which satisfy this condition, that Ex square and Ey square are finite, square integrable means both Ex square and Ey square are finite. Okay, then of course then expectation of x and expectation of y are finite, and then expectation of ax plus y is a times expectation of x plus y, but variance of ax plus y is a square variance of x plus variance of y plus twice covariance of xy. Okay, that's why I have mentioned the covariance here. Of course, if x and y are two square integrable random variable, then you have this inequality. Expectation of mode of xy is less than equal to expectation of x square into expectation of y square. So this is Cauchy-Schwarz inequality. You see this above inequality, I also said Cauchy-Schwarz inequality. So if you take a random variable y which is taking the value 1 with probability 1, then you get this inequality from this general Cauchy-Schwarz inequality. Now what happens is that, so this condition tells you that if x and y are two square integrable random variables, that is ex square and ey square are finite, then of course x into y also has got finite mean, and so we can define covariance of xy as expectation of xy minus expectation of x minus expectation of y. Now, if you think of what is covariance of xy, so you have two random variables x and y. You plot their values along the x and y axis, so you will get points on the xy plane. Now, in the xy plane, you could plot the point x bar y bar, or expectation of x, expectation of y. So this point will have x on the x coordinate the mean of x, and on the y coordinate mean of y. Now, if you are looking at the fluctuations of the point in the xy plane around this point x bar y bar, so that is captured by the covariance. Now, one important thing, variance is always non-negative, right? Because this is x minus expectation of x whole square. You can also see from this inequality, since ex expectation of x whole square is less than or equal to ex square, so this difference cannot be negative. Okay, but covariance can be both positive or negative. Okay, so that is an important point. On variance, now here I will not get into the other things. Moment, coefficient of skewness, cutoff is here. Let me continue my discussion with variance. What is I want you to figure this out. What is variance of x plus c? Variance of x plus c, where x is a random variable and c. So you can figure it out that this is equal to variance of x. So there is no effect of change of origin. This is simple. Expectation of x plus c is equal to expectation of x plus c. How this is coming? How I am getting this? So think of x as a simple random variable taking the values x1, x2, xk. Then what is x plus c? Then x plus c is again another simple random variable which is taking the values x1 plus c, x2 plus c and xk plus c with the same probabilities. So now apply the definition of expectation. So what will be expectation of x plus c? Then it will be the summation of xi plus c into the corresponding probability pi. Now you can easily write it as summation of xi into pi plus c times summation of pi, and summation of pi is 1, probabilities add up to 1. So that will give you expectation of x plus c. And variance, now in general also this is true, but let me not get into the general proof. The variance of x plus c, how is it true? How is it I am getting variance of x? It is very simple, that if you look at this formula, so variance of x plus c would be expectation of x plus c minus expectation of x plus c whole square, and then apply this one, that expectation of x plus c is expectation of x plus c. So then that cc will cancel out, and so let me write where c is a real number. Be here. Okay. Expectation of c is equal to c, and variance of c is equal to variance of a constant is equal to 0. That's also obvious, because you can think of this constant as a simple random variable taking only one value c. So then by that definition it will be c into 1, expectation of c, so that is c. And so therefore what is x, that is so what is variance of c, that will be c minus expectation of c whole square, right? So c minus c, that is 0. So that is it. So these are two simple but important things. Okay, variance of x, variance of x is non-negative. Okay, is non-negative. This is trivial from, and variance of x equal to 0 is implies probability x is equal to expectation of x with probability 1. So this is important. So what is the interpretation of variance equal to 0? You have a set of numbers. Variance 0 means all the numbers are equal, and in this case also similar interpretation, variance expectation of x minus expectation of x whole square is equal to 0. Now x minus expectation of x whole square is non-negative value, so its mean equal to 0 means it has to be 0 with probability 1. That is probability x minus expectation of x equal to 0 is 1, and so x is equal to expectation. Let me put this condition here, that if x is a non-negative valued random variable, and variance and expectation of x equal to 0, then probability x equal to 0 is 1. So important though that this non-negative valued random variable is the important issue over here. If you compromise this concept, then of course this result is not true, because you can think of a simple result. Suppose x is taking two values, -1 and +1, each with probability half. -1 and +1, each with probability half. Then what is expectation of x? Then expectation of x is -half into 1 plus 1 into half, that is equal to 0. But then you see this condition that I have written, that expectation of 0 then probability x equal to 0 is 1, that is true only when x is taking non-negative values. That means it cannot take any negative values. Now that is the last result is an application of this result, because variance of x equal to 0 implies expectation of x minus expectation of x whole square is equal to 0. Now x minus expectation of x whole square is a non-negative valued random variable, therefore this equal to 0 implies probability x equal to expectation of x is 1. So these are some important properties, definition and properties of variance that I want you to remember, and the next task would be exercise compute mean ex and variance of x for all the discrete distributions. Okay, thank you.